Hi, since we've introduced the exponential function in the last video, I found it very necessary to make a new video about some interesting aspects of that function. In today's video, we explore the hyperbolic cosine, the hyperbolic sine. We're going to see their relationship to the exponential function, and at the end, how they can find applications in real engineering. If that is interesting to you, please make sure to like and hit the subscribe button. Let's start. Have you ever paid attention to some type of functions and their shapes? Let's have a look on this function, for instance, y equals to x squared. For every x you consider on the x-axis, the corresponding y value is exactly the same as the one from negative x. We say that y equals to x squared is an even function. Now let's have a look at another function. You could do the same experiment for every x value in the definition domain, and the relation negative fx equals to f of negative x will remain true for this function. So as opposed to the function y equals to x squared, we say that the function y equals to 1 over x is an odd function. Before we continue, let me do a quick precision about how it's really important to know whether a function is odd or even. In fact, we use that information in mathematics in order to have a quick idea about how the graph of a function could look like. It also helps us to take faster decisions and move very fast by analysis. For instance, the integration trick. This is the most common use in calculus. Let's take an example of odd functions. If you integrate an odd function over a symmetric interval, the result is always 0. Because the area above and below the x-axis cancel out perfectly. The exactly opposite is true for even function. Instead of calculating from minus a to a, you can just calculate from 0 to a and then double the result. Another engineering field where it really matters whether the function is odd or even is by signal processing and Fourier series. Here, engineers just use this to wisely decompose complex signals into simple waves. Even signals contain only cosine terms because cosine is even, and odd signals contain only sine terms. We are going to come back to this in another video. Now the question, what if the function is neither odd nor even? Even if the function is not odd and also not even, there is always, really always, a way to find two functions, the one odd and the other even, whose sum gives us the original function. You aren't convinced? Let's check it out. Let gx be any function. The definition of an even function is gx equals to g of negative x. An odd function is defined as gx equals to the negative of g of minus x. If I add to a given gx value the image of negative x through the same function, I will obtain the following thing. We're going to call the resulting function h1 of x, which is gx plus g of negative x. You should agree with me that this is an even function, since we obtain exactly the same expression if you change the argument x to negative x. Now let's do the opposite. We subtract g of negative x from gx. We're going to call it h2x, which is gx minus g of negative x, which, as you guessed right, is an odd function since it becomes negative h2x if we change the argument x to negative x. The goal here was to split gx into two parts whose sum is gx itself. By adding h1x and h2x, we obtain 2 times gx. It is therefore necessary to divide both h1x and h2x by 2, and we will then obtain the desired functions that are even and odd part and whose sum is exactly equal to gx. As you may have guessed, the exponential function doesn't escape to this rule. It can also be split into two parts, one even and the other one odd. By applying the formula we've established above, we get the odd part will be the half of the difference between exponential x and exponential of negative x, while the even part emerges naturally as the half of the sum between exponential x and exponential negative x. I'm quite sure you've already seen this expression somewhere, like the half of the sum between exponential x and exponential negative x, and the half of the difference between exponential x and exponential negative x. Well, let me tell you something, your intuitions are right. These functions and expressions exist, and in the majority of books, they have been described as the hyperbolic sine and hyperbolic cosine. But now you might ask yourself, what does the exponential function has to do with hyperbolic functions, and why sine and cosine what are they doing there? Yeah, I know, that's really crazy. I also asked myself that question, but don't worry, we're gonna break it down. In order to understand hyperbolic cosine and hyperbolic sine, we first need to understand cosine and sine, what they actually are, what they actually do. Let's consider an angle, theta for instance, between 0 and 2 pi. For each theta in this interval, 0 to 2 pi, let's compute the cosine and the sine of theta. We have this array. We choose to represent on the x-axis the value of cosine theta and on the y-axis the value of sine theta. As we represent all the points, the emerging curve is naturally a cycle. You will notice that for each point, the triangle formed by the point, the axis, and the origin is a right triangle. Therefore, the Pythagorean theorem can be applied. By doing that, we have cosine theta squared plus sine theta squared equals to 1, since we have a unique cycle. This relationship is true for every point on the cycle independently of theta. It's the general definition of the cycle. Now let's observe the area aspect. The area of a full cycle is pi times r squared, where r is the radius, in our case 1. So the area of our unique cycle will be pi. For a given angle theta, the portion of the cycle representing that angle will be theta over 2 pi. So when trying to find the area of this specific portion of the cycle, we just have to multiply the area of a complete cycle by that constant. We can conclude that in a unique cycle, the area of the sector is half the angle. Keep this formula in mind, it will be important for the analogy with the hyperbolic curve. Now let's do a similar experiment for the exponential function. If we consider the even and the odd part of the exponential function and plot them in the graphic as x and y coordinate of some points, so that the x-axis represents the even part and the y-axis the odd part, something really interesting happens. As we represent all points, the emerging curve is a hyperbola. This is exactly the key. For each point given by the coordinate x and y, yx represents the hyperbolic cosine and y the hyperbolic sine. The relationship between x and y is given by x squared minus y squared equals to 1. This is true for every point independently of t. Now let's observe the parameter. In a circle, the parameter was the angle theta. In a parabola, an angle doesn't make any sense, so we used a parameter that we call t, where t can be defined as twice the area under the curve from the x-axis to the point. This gives a natural geometric meaning for t, and it's the same analogy to the angle in a cycle. Now that we've seen the exponential function can effectively be split into two parts, one even and the other one odd, we can now give them their name. We call the even part of the exponential function the hyperbolic cosine and the odd part of the exponential function the hyperbolic sine. They are nothing more than two parts of the same function. Yeah, that's just what they are. What is also really interesting is that these two functions are not just basic and random or crazy. What is also really interesting is that these two functions are not just abstract mathematics. They appear in real engineering and in the nature, and helps us solving not real problems that we face in real life. A well-known example is the hanging cable, like the power transmission line between two towers. When a cable hangs under its own weight, its shape is described by the hyperbolic cosine. So engineers use this to design power line. They know that the length of the cable changes with temperature. In summer, for instance, the cable becomes really longer and goes down because of the heat. And in winter, the cable becomes shorter and the tension increases. Using the hyperbolic cosine that most describes the shape of that hanging cable between these two towers, engineer can have then precise information about the minimum and the maximum height of the cable, as well as the tension, and can then place the towers as the right distance so that the cable never goes too low and never breaks. Another example appears in dam engineering and hydraulic power plants. As we go deeper in water, the pressure increases. So engineer must find the way to design the dam so that that pressure gets safely redirected into the structure and the ground. The distribution of forces and stresses in the dam can be modeled using functions related to the exponential and the hyperbolic functions. This allows engineers to predict where the forces are the strongest and then design the shape of the dam so that it remains stable. So guys, we've reached the end of the video. Hope you had a lot of value, learned a lot of new stuff, and also appreciate the video. If it's the case, please don't forget to like and hit the subscribe button so you don't miss any video. And I'm willing to see your questions in the comment sections. See you in the next video.